Okay, let's proceed with second example using plane frame again, but this time sway frame, so that this is more general. Okay. And this is our model here. So loading. We have 30 and 40. No, I'll return this to this one. So I'll make this negative 18, modify, yes, and 40 lateral load. Then run again, save. Yeah. Okay, so this is the problem. 10 meters, 10 meters. The inertia is 300 times 10 raised to 6. So I assumed an area, a cross section, no? Where's that? 300 times 10 raised to 6. Where's that? That one. So this is the inertia. So I assume a 300 width beam. So BH cube over 12, I got 228.943 as depth. And multiplying the depth and the width, I got 68,400. Sorry, 228. Yeah, 68,400. Okay. So I implemented that here. So properties 0.228943 by zero point 0.3. Okay, so to be consistent. Okay, so this cross section has a 300 times 10 raised to 6 mm to the fourth inertia. Of course, this is steel, no? As you see here. Okay, and loading, we already checked that, and I already run this. So post processing. But okay, by the way, let's discuss the coding. So how's the coding? So this is a 3-member. This is member 1, member 2, member 3. So this is 1, 2, 3. This is 4, 5, 6, and then 7, 8, 9, then 10, 11, 12. Okay, and now for member 1, so 1, 2, 3, 4, 5, 6. Okay, consistent. For member 2, 4, 5, 6, 7, 8, 9. 4, 5, 6, 7, 8, 9. Okay. For member 3, so remember my convention in column is down, up. No? So I will start here. 10, 11, 12. 10, 11, 12. 7, 8, 9. 7, 8, 9. Okay. Now, since this is a sway frame, we expect there will be a rotation here and a sway. So actually, all the degrees of freedom, these three displacement will be activated. Okay. So that makes it a general problem. So therefore, our unknown is 6. So our S is 6 by 6. Therefore, we will need 4, 5, 6, 7, 8, 9. So all stiffness matrix with this code will be required, will be extracted. So for member 1, that's why 4, 5, 6 is encircled. For member 2, everything is encircled. For member 3, 7, 8, 9. Okay, that makes my BU matrix for member 1, the 4th, 5th, and 6th element. For member 2, all element. For member 3, the 4th, 5th, and 6th element again. Now, what's the location of that? So that makes our BB matrix. 4, 5, 6 will be first, second, and third. Right? For member 2, this one occupies the 6th element. For member 3, 7, 8, 9 occupies the 4th, the 5th, and the 6th. The 4th, the 5th, and the 6th. Okay? So that's why this is our BB matrix. Right? 4, 5, 6. Okay? 1, 2, 3. 1, 2, 3, 4, 5, 6. 4, 5, 6. So my null matrix is 6 by 6. Okay? Consistent. Now for the length, 10, 10, 10. They are equal in length. Inertia, equal in inertia. The theta, so pi over 2 because 90 degree, 0 because horizontal, and pi over 2 again because 90 degree. Take note, our orientation is from here going here, so that's pi over 2. In case you you reverse the coding such that you started here, this will be negative pi over 2. Okay, take note of that. That's why I made this my convention, so that my theta will be positive pi over 2. Okay, so this is our area, and here's the implementation. And take note, I changed the looping to 3 because we have 3 members. So this is the S matrix, and this is because we have both P matrix and P sub F, right? Where is our P matrix here? I think it's in the other here. So this is our P matrix because we have a joint load applied, the 40 kilonewton one. Okay, remember P matrix is the joint load, while P sub F came from the Q sub F. Okay, so our Q sub F is this one. Okay, WL over 2, WL squared over 12, 90, 150. Okay. Okay, 90, 150. Then combine P minus P sub F. This is the combined P minus P sub F. So it should be consistent here. P minus P sub F. So I have a separate vector for P and a separate column vector for P sub F. Okay. So this should be 90. Wait. 150. 0, 90, and negative 150. Okay, so this is the displacements. Okay, So V sub 1, D1, D2, D3 is for this one. And for member 2, we have all displacements, okay, because this is member 2. And for member 3, we only have this as the displacement. That's why D4, D5, D6. Okay, then applying the same formula for the fixed end forces, we get this. Okay, let's check Verstaal if beam results. Okay, so let's check member 2, shear bending. Okay, so these are the forces for member 2. So we have, this is bending, so this is code 4, code 5, code 6, so 6, 14. Okay, then negative 185, that one. Alright, how about the shear? So we have 72 and 107. So 72 and 107. Okay, so the same for the axial, that's the FX 34.97. So I got 34.99. Okay, so for the column, shear bending 6414, that's member 1. Oops, got 6414, 6414. Okay, for shear 5, so 5 and 5. And for axial, it's 72 fx of x, so that's 72. Okay, so last for member 3, 164 185 for the bending, 164 185 for the shear, 34 or 35. Okay, same. And for the FX, 107. 107. Okay, so that's it. So you can use this SMAT code to analyze a frame, non-sway or with sway. So let's assume, let's try to edit the model. So since this is a metric frame, I'll remove the 40 kilonewton. No? Okay. So I'll delete. So in order to not delete totally, I'll proceed to the stud editor and just make a comment to make the 40 kilonewton for the stud to ignore this. Save, close. Then run. So here in our SMAT, what shall I do? What modification will I get? So it's the same BU and BB, no? Because we only changed the loading. So I'll just remove 40 here. Just make it 0. So I'll remove the lateral 40. That's it. And let's see the forces. member 1, 49.99. Okay, 49.99. Same for the shear, 14 or 15, 15. Okay, for the axial, I okay, post processing beam results. For the axial, it's 90, so it's 90. Okay, then for member 2, shear bending, 99.99. Okay, 99.99. For the shear, 90, 90. And for the axial, it's 15. Take note, this is a non-sway frame. So this code is general. You can analyze both sway and non-sway. Okay, because that's the advantage of using plane frame stiffness matrix. You can analyze both sway and non-sway frame. Okay, without tweaking the stiffness matrix such that making the the code here, say this is code 3, then this is code 6, and make this equivalent. So okay, that's the advantage. Okay, it's direct, no, you can directly get the action, no, and you can uh, analyze both sway and non-sway. However, the stiffness matrix becomes larger, okay, compared to just using a 4x4 beam stiffness matrix. Okay, so that's our topic for today.